We're going to start the new chapter, chapter 3. Here we discuss the applications of the first order differential equations. So we get here three types of applications. We're having the orthogonal trajectories, we'll discuss the growth and decay, and we discuss Newton's law of cooling. So I take a very small example. I have given a function f(x, y, z), let's say constant equal to 0. I find dy by dx of this one. The slope of the line is equal to fxy. And then I find another curve such that when we take the slope of that one is such that is here, for example, this is my m1, and I find the other curve g, x, y, and c1 equal to 0. I find dy by dx of this one is equal to minus is m2. I say if I have this slope m1 into m2 and the product of this slope is minus 1, it means these two slopes, two tangents are orthogonal. If they are orthogonal at every point of the intersection of the curve, we say this is orthogonal trajectory. I take an example for this one. I have the straight line y equal to mx. I take the derivative of this one. I get here dy by dx is equal to m. I put the value of m. I get here dy by dx is equal to, we get here m is y upon x. So is y upon x. This is my equation 1. This is my m1. So my m1 is y upon x. This here number 1, this is example 1. I take here, this is my fxy, c equal to 0. Now number 2, I take g, xy, c1 equal to 0. That is x square plus y square is equal to c1. I try to find the slope of this one. I find the derivative of this with respect to x. I get here 2x plus 2y dy by dx is equal to 0. I find the value of dy by dx. So 2y dy by dx is equal to minus 2x. I will get here dy by dx is equal to minus 2x over 2y, and I get minus x upon y. So my slope, here I have the slope, m1 is equal to y upon x. What's my m2? m2 is minus x upon y. So if I take the product of m1, m2, so it is the product of this m1, m2. My m1 is y upon x, and my m2 is minus x upon y. The result is equal to minus 1. So we say the lines passing through the origin and the circle for different values of c centered at the origin, they are orthogonal trajectories. Let me see here. This is my y-axis. This is my x-axis. This is my x-axis. This is my y-axis. And I take a line passing through the origin. For example, I take this line and just try to make a better picture of this one. I remove this one and do it again. I have this line passing through the origin, and this line passing through the origin, and I am having a circle. My circle is centered at the origin, maybe diameter equal to 1. Here is diameter equal to 2. So there, where they're intersecting the line in the circle, we can see here we get tangent to the circle and this line. So this slope is 90 degree. I take it tangent to the circle, this line. I take tangent to the circle and this line. I take tangent to the circle and this line, because slope of the line is given to us. They all are orthogonal. So we say they are orthogonal. We can have more lines, we can have more circles, and they all are orthogonal. So we say that the circles, straight lines, straight family of curved straight lines passing through origin, passing through origin, and is number 1, and circles center at the origin, they are orthogonal trajectories because they are intersecting, and there is angle of the intersection of these two is orthogonal. So we can have here, this is 90 degree, all of them. So we say they are orthogonal trajectories. So we can find, just I take a very small example. We're given an equation and we need to find the orthogonal trajectory for that one. That's the method we're going to discuss for the orthogonal trajectory. Then we come to here for the growth and decay. So I have this graph. This is my y-axis. This is my x-axis. I'm having a curve here, exponential curve, and this curve is like this. It's coming here. And I have another curve coming like this, and going like that one. Now I'm having this exponential curve. This is my time, and this is my y, and I get here e to power kt. Here I say k is bigger than 0. We say this is growth. And here also e to power kt, but k is less than 0. We say this is decay. So we will find the solution such that if k is bigger than 0, then we have the growth. If k is less than 0, we have the decay. Then is the Newton law of cooling. Newton law of cooling is like that. I take the rate of change of the temperature, how the temperature is changing. I take T is the temperature and small t is the time. I say this is proportional to the temperature of the body and temperature of the surrounding. For example, it's hot weather and I have a cup of tea and put this cup of tea whose temperature is about 80 degrees centigrade outside where the temperature is 50 degrees centigrade. The difference between these 80 minus 50 is 30. So when you say the change is very slow. If you take this hot water and put it in the refrigerator where the temperature is minus 10, so difference is 19. So the temperature is decreasing very fast. So we say the rate of change of temperature is proportional to temperature and the surrounding we are putting. So this is the idea, and these are all are described by the differential equations of the first order differential equation. We can see this is the first order differential equation, that's first order. And here also we have described, and here this growth and decay, we say the growth and decay, that is dy by dt is proportional to the y. Y is the quantity present. Y eta is a big quantity, if the change will be bigger, small quantity change smaller, as proportional, directly proportional to this one. And then we can write here, this is my dy by dt is equal to k times y. So this is my equation for the growth and decay. If k is positive, we have the growth. When k is negative, we have the decay. And then we solve this one. Also, we solve this one for t. And we are having here dy by dt. We want to find the other, we have given this curve, and we want to find this curve by using the idea of the orthogonal trajectory.